when you're finding magnitudes, you can just use the magnitude formula that I went over in the previous lecture. Like if you're given that V is equal to, say, AB, like that, the magnitude, and I like to denote magnitude with double bars, not single bars like our Briggs textbook does, but you know, it's a matter of style. You're just going to take the square root of the sum of the squares, and this is magnitude right here. Magnitude is length. Okay, so then what? Well, what if somebody said, I want you to find the magnitude of a scalar multiple of your vector? Well, you could do it in two ways. One way would be the slow way, where you go, okay, let me distribute this scalar C. Remember, scalars are just pure real numbers. And then the new magnitude will be the square root of the sum of the squares of these components here. And that'll give you the right answer. Kudos, you got the right answer. But there's a quicker way. The quicker way is don't distribute the scalar and just immediately do the following. Take the absolute value of the scalar, because in case it's negative, you definitely want your magnitudes to be positive. So you're going to ensure that it's positive. And then just multiply that absolute value of your scalar with your original magnitude. Boom. And that will give you the magnitude a little bit more quickly. That's all. It's just a nice theorem to have. We don't use it that often, but when it does come in handy, it's nice. It's beautiful. Okay, now a theorem that will come in handy a lot. You'll love this one. I love it. Unit vector pointing in the same direction. What the heck? What's a unit vector? It's a vector that has a magnitude of 1. So from now on, anytime somebody says a unit vector, you will just immediately in your mind go, oh, that vector has a magnitude of 1, a length of 1. They call it a unit vector. Fine. If you need a unit vector pointing in the same direction as some given vector, here's the quick and dirty way to get it. So start with the original vector, and you'll be given some format, component form here, non-zero. Then the vector they're calling u, which is the original vector divided by his magnitude, is going to be, I'll do this in slow motion. So you first have your vector, v1, v2 components. You're going to divide that by the magnitude. And then you distribute this scalar over your components. And we're done. And we'll do an example in a moment, so don't worry. That's it. And that will give you a unit vector that's pointing in the same direction as your original vector. All that's saying is that it's going to shrink or stretch, depending on the case may be, your original vector so that it has a length of 1. This does it for you, which is nice. And this semester, we're going to be needing unit vectors a lot, like all the way through the whole semester. So it's important to know how to do it. Here's some vocabulary. When you multiply this vector by this scalar, 1 over the magnitude, a lot of textbooks call it normalizing. They go, oh, normalize the vector. I don't like that terminology because the word normal in this class is going to have multiple meanings, and that can be confusing. So in my class, I'm going to call it unitizing. That's not in any textbook, though. I didn't make it up. My mentor, Professor Arnie Vallone, may he rest in peace, RIP. He taught me that when I took his course, unitizing the vector. That'll mean find a unit vector pointing in the same direction as the original vector. Okay, let's do it. Here's an example. They give us a vector, and part A, find a unit vector that points in the same direction as V. Now, before I do that, I'm gonna sketch the vector V. Okay, so here's the x-axis and y-axis. How do I sketch this vector? Does anybody remember? Where do I start? I'll check
Yes.
the chat. Does anybody want to?
Yeah, so you go 3 to the right, because for the
Mhm.
first one's gonna be the x-axis, the other one's gonna be the y-axis. So you go 3 to the right.
Perfect. Yes. Then,
And then the arrow will be going downwards, right?
okay, that is very true. And how do I get that arrow going downward? Like, would I just point like this? This is an arrow pointing down.
No, you have to do it from the -1.
Yeah,
down.
very good, very good. Yes, exactly. The -1 on the y, and then you'll find the point 3, -1. So there's the point 3, -1. How do I get the vector 3, -1?
You draw a line through the origin, the
Mm-hmm,
origin to the point.
mm-hmm. Yeah, you draw the little arrow, huh? That's not very straight, but I think you get the idea. Yes, perfect. Thank you. Yes, perfect. There is the vector 3, -1. Now, it doesn't have a magnitude of 1. It is not itself a unit vector. Well, how do you know? Well, let's actually go find the magnitude of this vector, because we're going to need to anyways, due to the fact that when you unitize a vector, you divide by its magnitude. So let's go ahead and get the magnitude. And the magnitude is square root of 10, which is 3 plus a little bit of change. So fine. So when they're asking us to find a unit vector pointing in the same direction as the original, what's going to need to be happening is we're going to find a vector that's only got a unit length there, that's pointing in the same direction. So we're going to use this, and we're going to use this theorem here because it tells us how to do. So I claim that the unit vector, we'll call it u, pointing in the same direction as v, is v divided by v's magnitude. Okay. Now, the Pearson MyLab Math lets you get away with this being your final answer. I won't. I'm going to take a couple points away. Well, what if MyLab Math gave me full credit? I deduct the points. I'm sorry. I can either give points or deduct points. So here, I'm just asking you to make me completely happy, and you'll thank me later when you get to other problems. Distribute the scalar and finish the problem completely for me.
I have a question.
So this answer is what I would like. Sure.
Are we going to be expected to rationalize the denominator of these answers, or can we just leave it as like 3 over square root of 10?
Excellent question. The answer is you don't have to rationalize your denominators in my class. Leave it just like this. Now, if you're the kind of person who, well, I like all my denominators to be rationalized, then be my guest. Go ahead and rationalize it. I don't give you any extra points for it. MyLab Math will still mark you correct, whether you give it this way or the rationalized way. You don't get any extra points. So don't waste any time since I don't require it. Does that answer your question?
I was just wondering because some professors prefer it that way, so I was just making sure.
Absolutely, and that's why I think it's an excellent question, because you always want to find out not only how to get an answer, but the format that that professor might prefer. Because, you know, half the battle in college is learning the material, and the other half the battle is figuring out what makes that particular teacher happy, right? Okay, so let's do letter B. Find a unit vector that points in the opposite direction of V. Ooh, good news. You already did half the work. All you have to do for letter B is take the opposite of your U unit vector. Really? Yeah. So you're going to take the opposite of the answer you got for part A. So what does that mean? Well, negative means basically multiply by the scalar of -1. So finish out the problem for me and basically change the sign of the components, and boom, you're done. And there's the answer to letter B. Congratulations. Now, these two. Letter C, we want to find a vector that points in the same direction as V, but has magnitude that is 8 times more than V. So that means whatever the magnitude of V is, which is, you know, we got square root of 10, you want a vector that's 8 times as long. So it's going to be pretty darn long, probably even longer than that. I just don't have room. That's 8 times v. So letter C is real easy to get. You're just going to go 8 times the original vector, and that will give you a vector that has a magnitude that's 8 times more. Don't forget to distribute your scalar. And we're done. And there is the answer for letter C. That will give you a vector that's 8 times as long as V. Guaranteed. Now, letter D sounds like they're asking for the same thing as letter C, but don't get confused because they're not. Really? They want you to find a vector that points in the same direction as V, whose magnitude is exactly 8. Very different than 8 times as long. Don't get confused. Because you'll get the wrong answer. So step 1 is you first unitize your vector. So you shrink it down to its unit length. And then your step 2 is going to be multiply it by this magnitude that you want. So we'll multiply the step 1 result by 8. Now, good news, I already did step 1 when I did part A. We unitized our vector, we shrunk it down so that it only had a magnitude of 1. And so what we're going to do is we're just going to skip all the way to step 2 already. We're going to take 8 and multiply it with our unit vector. And don't forget to distribute your scalar. And as Lewis asked, we don't have to rationalize denominators. I'm okay. Just leave it. We're good to go. Perfect. And that's the answer for letter D. This vector has exactly a length of 8 units. Very different from 8 times as long as V. I hope you see the distinction. Okay, now let's do the theorem, the triangle inequality, just quickly. This is just a nice theorem. It's kind of obvious when you look at a picture, but it's good to know. Okay, it basically says that when you take the sum of 2 vectors and then you take that magnitude, so first you find u plus v and then you take that magnitude, that's always less than or equal to the sum of the magnitudes, the sum of the individual magnitudes. It's like, okay, yeah, so what? You know, it doesn't mean anything to me. Well, maybe a picture will help. Suppose you had u, and we'll use the tail to tip method. And let's say here's V. His tail is standing on the tip of U. And the resultant vector U plus V, if you remember from last time, is connecting the tail of U to the tip of V. There's U plus V. Can you see that the length of U plus V is going to be a little shorter than the sum of U, the magnitudes of U and V? And here's how we can do it. Like, let's say, here's your house, and like over here is the school, okay? The shortest way to get from your house to the school is to take the shortcut, just the path U plus V. That's the shortcut. And that's always going to be overall shorter than you taking this long scenic route where you take this road and then with the magnitude of U, and then you take the magnitude of V and add them together. So that's going to be a little longer path. So the triangle inequality makes sense. And then you've got a little triangle here. Yay. When do you have equality though? Because this is symbol here is a less than or equal to sign. I claim it'll be equal if the picture looks like this. Here's U, but V is pointing in the same direction as U. So V is like this. And that sure doesn't look like a triangle anymore. I know. It's a deformed triangle. In this case, you will have equality because U plus V's magnitude will just be the same as the magnitudes of U and V added together separately. So this is a deformed triangle. Somebody squashed it with their foot, smashed it. Not very interesting, but you get equality. All right, new topic. Well, wait a minute. Before I do new topic, we're going to play Kahoot. So what I'd like you to do is I want you to log into kahoot.it. And we're going to play a little game. So if you have a cell phone, I know most of you have a cell phone. If you have it handy, if you could please get it now and log into www.kahoot.it. And what you're going to do after you log in there is you're going to enter in a PIN number, okay? And the PIN number will come up on the screen in a moment. So once you enter the PIN number, then you can enter in your username, and you don't have to put in your actual name because you can use a fake name if you're embarrassed. So I'm waiting for the players now. Okay, let's play the game. Are you guys ready? This is really easy. It's all multiple choice, okay? Which one of the following fun facts about your professor is false? False, people. She was in a flamenco dance troupe for a few years. She has 2 children. She has been to Egypt, Greece, and Italy. She is certified in scuba diving. Go. All right. There's a majority who got it right. I do not have 2 children. That is correct. All the other ones are true. That's right. I know, weird, huh? Okay, let's see who's on top on our scoreboard. By the way, these points don't matter, and I didn't make up the points either. That's a Kahoot thing. Whoever is Kale is winning, 869, followed by Kobe, Jammin, and then a person K, and then Y. And let's keep going. Okay, question number 2. A vector consists of both magnitude and direction, velocity and direction, magnitude and velocity, speed and magnitude. All right, most of you got it right. Magnitude and direction. Good job. Fantastic. Those are the 2 properties a vector has. Okay. Jammin's on top, then Kale, then Y, then K, then Carlo. Kudos. What does a scalar consist of? Yay, magnitude only. Direction is something that a vector has. Vectors have a direction. They're pointing somewhere. Scalars are just pure real numbers. So a magnitude is a length, which is a pure real number. Okay. Yes? All right, who's our new leader? We still have Jammin, Kale, K, Kobe's on a streak. Carlo, congrats to all. Keep going. Key difference between vector and scalar quantities. Direction, yay, perfect. Yeah, scalars don't have a direction. They don't point anywhere. They're just a pure number, okay? So that's the key difference, because a vector has both a scalar quantity associated with it, that would be its magnitude, and it does have a direction. Yeah. All right, who's our new winner? Or Jammin's on top still. Kale, K, Carlo, Clayton. Kudos. Move on. Let's test your knowledge. Is this quantity a scalar or vector? Time. Woohoo! Most of you got it. Yay! Scalar. I know, but time has a direction. It goes forward. Oh, does it? I know. I'd like to turn back that clock. Let's relive yesterday. No, let's not. All right, who's got the leader there? Jam and Kale, K, Carlo, J. Congrats. Let's move on. Number 6 is force, is scalar or vector. Woohoo! Correct. It's a vector. Yeah. Yeah. Forces are vectors. Jam and Kale, Carlo K, exoms. Congrats. Keep going. Is distance a scalar or vector? Yay, distance is a scalar because it's a length basically, so it's a pure number. I know. Jam and Kale, KJ, exoms. Kudos. 8 of 12, we're getting close. Is temperature a scalar or vector? Yay, it's a scalar. It's basically a pure number. Yeah, it doesn't have a direction. K, Kale, J, exoms, A. Wow. Okay, new leader. 9 of 12. Is velocity a scalar or vector? Yay, velocity is a vector. It does have a magnitude, which is also known as speed, and it does have a direction. K's on top, Kale, J, exoms A. Congrats. Is mass a scalar or vector? Yes, it's a scalar. Woohoo! K, Kale, J, exoms A. Getting close. 11 of 12. What's this method of adding vectors called? This one's a little tricky. Head to tail, sometimes called tip to tail or tail to tip. Yep, yeah, that one was a little bit tricky. Kale, J, AK, and Jammin. Okay, we got one more, and this will determine the grand champion. Remember, these points don't matter, okay? Don't get worked up. Last one. A vector has initial point 3, 7 and terminal point 3, -2. Find its component form. Okay, the correct answer is 0, -9. Remember, when you are given an initial point and a terminal point, order matters. You guys have to do terminal minus initial. Terminal minus initial. So the terminal point's x coordinate, which is 3, minus the initial point's x coordinate, 3. 3 minus 3 gives you 0. So that's the first component of your vector. And then you subtract -2, the terminal point's y coordinate, minus the initial point's y coordinate, 7. -2 minus 7 for a grand total of -9. So that would be the answer, 0, -9. Congrats, and let's see who the grand champion is. In third place, Carlo, yay! Second place, hey! First place, Kale. Woohoo! Runners up, Jay and Exoms. Congrats to everybody. Woohoo! All right, I was getting into it. This music actually sucks, I know. It's annoying, right? All right. So what do you think? Did you guys get something from that at all, or a little bit? Have some fun? Good game? Good game, GG, good game. All right. All right, let's do some more fun. We got some more exciting topics here. Standard unit vectors. What the heck is it? This is how our physics folks like to write their vectors. Okay, so we're going to finally get into that. The unit vectors, what's a unit vector? Tell me in the chat. Unit vector is, I already forgot, I get it. Have some more coffee. Vector with a length of 1, fantastic. Good, we got more than 1. Yay! Vector with a magnitude of 1. Got it. Perfect. These two vectors, 1, 0, and 0, 1, those are special unit vectors. They're called the standard unit vectors. Really? They're standard. Yeah. The first guy's name is I, the second guy's name is J. And the key fact is that any vector V can be written as a linear combination of the standard unit vectors. So here's how. Let's say you're given a vector in component form, angular brackets, A comma B. If you retro engineer this, basically, using your knowledge of scalar multiplication and vector addition that we've done previously, you can write this vector AB as the scalar A times the vector 1, 0, plus the scalar B times the vector 0, 1. But that's going to be A times this new vector I like to call it I hat, plus B times the vector J. And I use these hats only for the unit standard vectors. I will be okay if you do the little arrows that we talked about last time when we did how to denote vectors with the little vector thing on the top. Either one of those is fine. This is the alternate way to write a vector. And it's used in our textbook as well as all the physics textbooks. Okay, so quick review. What's the other form of writing a vector called that we've studied so far? Starts with a C.
Component?
Yes, thank you. Component form, yeah. And this is the new way, linear combination of the standard unit vectors. That's a mouthful. I wish there was a quicker name for it. I don't know what the quicker name would be. I'm looking for one. All right, let's do an easy peasy example. Here are 3 vectors that are all in component form. Your job is to figure out how would you write these as a linear combination of the standard unit vectors. Let's just do this. It's easy. The first one, you would go 3 I hat, it's a hat, plus -4 J hat. But because adding a negative is the same as subtracting, I would accept 3I minus 4J. That's also legit. They're both fine. Same thing. Letter B. 0 I hat plus -2 j hat. But 0 times anything is 0. So get rid of it and just write simply -2 j hat. 7, 0, 7 I hat plus 0 j hat, but scalar multiple of any vector, just going to zero it out, get rid of it, and you'll just write it more simply in abbreviated form, 7 I hat. And we're done. See, that was easy. New topic. Let's talk about resolving a vector into its components once you're given a magnitude and a direction. And theta is going to be a direction, where theta is going to be the angle that a vector makes with the positive x-axis. So v equals blank, comma, blank. What goes in those blanks? Well, hold on a minute. Not so fast. Let's slow down. Let's draw a little picture. So let's say you had some vector v. I'm just going to draw some generic vector v. And somebody gave you his length. So you're given this magnitude of v, something, I don't know, 10, whatever. And somebody tells you the angle theta here that the vector makes with the positive x-axis. You have that in hand. So your job is to figure out the x component and the y component of this vector. I don't know, can I guess? Not a good idea. So the trick is, if you drop a perpendicular of the tip down to the x-axis, and you notice we have a right triangle here, where the leg down here on the x-axis, that length is the x component we need, that's the unknown. The height of this leg here, that's opposite the theta, is the y component, unknown. And the hypotenuse, you already know, it's given. Good news, you already know that. They gave it to you. So then how do you get the x and the y? We're going to use some trigonometry. So hopefully you remember from your trigonometry days that cosine is equal to adjacent over hypotenuse. So what does that mean for us? Well, cosine theta will be the adjacent side leg, which is x, all over your hypotenuse length, but you know that, it's the magnitude of v, and then solve this little formula for x. And that's easy because you'll just multiply both sides of this equation by the magnitude. And there's your x component. So I'm going to fill in this blank here. And there you have it. Sine theta is opposite over hypotenuse. And for our little right triangle, we have sine theta. The opposite side leg is y. And you know your hypotenuse, it's still the magnitude of v. Solve this little formula for y. And you'll get your y component, given the magnitude and the direction. So fill in the blank up here. And you have it. Yay.
You could just do the Pythagorean theorem, right, for that third side. It's a lot quicker.
Well,
Or does that not work?
That's true. That's true. And in this problem, they're not giving you the x and the y. They're giving you magnitude already in hand.
No, I'm saying like when you find the x and then you can just use it to find the y.
Oh yeah, once you've found the x, you can use the Pythagorean theorem to find the y. Sure. But I probably won't give you credit for that if you do that on one of my quizzes or exams in this class. Why not? Because I want you to know that. I don't want to see a radical involved. It's going to be pretty messy. Your calculations might get a little bit yucky if you do it that way. But I see your point. But I'm going to encourage you to use this formula. I'm going to do one of these problems, and then you're going to do one with a buddy in about 2 shakes. So take a look here at example 5. Suppose you're told that the magnitude is 4. Okay. And they gave you a direction. That's just the angle that the vector is making with the positive x-axis, 30 degrees, fine. Find the component form for v, fine. So what you know is the x component will be 4 times cos of 30 degrees. And if you forgot what cos of 30 degrees, don't worry, because I included something really nice for you down here. This unit circle that you probably saw in a trig class sometime. And if you look at 30 degrees, the unit circle point there, the x coordinate square root of 3/2 is your cosine. And then reduce this to lowest terms, and I get 2 root 3. And then the y component is going to be 4 sine 30 degrees. So that's 4. And let me look at this unit circle again. What the heck was the, oh, it's a half, yay. Reduce, and now put it all together. So the component form looks like 2 square root of 3 comma 2, and you're done. Now, if they had asked for
Oh, one second.
vector and linear combination of standard unit vectors, you would have gone, okay, well then v is going to equal 2 square root of 3i hat plus 2j hat, and you're done. Either way. Now, usually when you're doing your homework on MyLab Math, it will tell you if it wants component form or the linear combination format. So you'll know. Okay. So you guys ready to try one? So you and your buddy are going to do example 6 for me. Yay.
Give me PTSD.
PTSD after doing this problem. I'm sorry.
No, it's chill.
So how many people got that W is equal to 4 negative 4 square root of 3? Did everybody get that?
Yes.
Yes.
Oh, good. I'm glad to hear it. That's awesome. Perfect. Okay, so if you didn't, the idea was you're given the magnitude, that was 8, and you were given a direction that it's making with a positive x. And so all you had to do was use this idea of the formula I gave you. Here's your x component with 8 cos 5 pi thirds, and then 8 sine of 5 pi thirds was the y component. And then you had to go, uh-oh, if you forgot what cos and sine of 5 pi thirds are, not to worry, we got it right there, right? You got this unit circle diagram. It's helpful. I know, you're welcome. So, you know, you plug that stuff in, you got the cosine is a half, and then the sine was negative square root of 3/2, and then you always want to reduce. And so you reduce, and I'm going to have to kill my bird in about 2 seconds. No, see, you have to be quiet, otherwise you're going downstairs. Sorry. So there we're done, okay? Let's talk about going backwards. So we were going forwards then. So the going forwards, just remind you, if somebody gives you a magnitude and somebody gives you a direction, you can get the components. But what if you have to go backwards? So somebody gives you the components, but they want the magnitude and the direction. How do you do that? So here's the deal. You already know how to get magnitude. We did this already. So the only question is, how do you get the direction if you're given the components? Okay, so you're going to use this formula here. Theta is equal to arctan, or tan inverse y over x. Why does that work? Let's just see here. Here's your vector v, and they're giving you the x and the y. So if I drop a perpendicular down here and we look at this right triangle again, you know what the x is and you know what the y is. You have that in hand. So obviously you know how to get the hypotenuse, because that's just the Pythagorean theorem, which in fact is the same as the magnitude formula. That's the Pythagorean theorem in action. So how do you get this theta here if you have the x and the y? Well, we know that tangent of theta is opposite over adjacent. And so you have the y, that's the opposite, you have the x. And if you take tan inverse of both sides of this equation, like so, you've probably seen this in a trig class, you get that theta is equal to tan inverse of y over x. Okay, now, big caveat about this formula. It won't work if your vector is in quadrant 2 or 3, the tip of the vector. Yeah. Why not? In standard position. Something that you learned in Calc 2. In Calc 2, I hope you recall that if you had y equals tan inverse of x, that the range is y has to be in this interval, negative pi halves to positive pi halves. That has to be true. So we all know that positive pi halves is, 90 degrees, and negative pi halves, negative 90 degrees. So as long as your vector lives in this interval, which is quadrant 1 and quadrant 4, this formula works perfectly. But if your vector is over here in quadrant 2, it's not going to work so well. You're still going to use it though. What are you going to do? You'll add 180 to the answer to get your actual direction. So let's do some examples so you can see this happening. So in case you're confused, okay? So here's a nice vector, components 1, 2. What quadrant does this vector lie in?
First quadrant.
Good. And so if you graphed them, you would find the point 1 and then the point 2 on the x-axis and the point 2 on the y-axis. You would graph 1, 2, and then you would graph an arrow going to it. So it's clearly in quadrant 1. So the formula is going to work fine. Let's get the magnitude first because that's easy peasy. I get square root of 5. The direction, which is the angle, and that'll be arctan or tan inverse y over x. Be careful you don't accidentally do x over y. That's a common silly mistake that students make when they're in a rush or doing an exam or something. So when you go to your graphing calculator and you're going to do this, I encourage you to first make sure that you are in degrees mode, because when you get an arctan, it's kind of yucky to get it in radians, okay? I'm already in degrees mode, which is good. So I'll just hit enter or second quit. And then I'm going to go second arctan 2, and I see 63 point whatever, and they said they wanted us to round it to the nearest 10th of a degree, and that will give us 63, oops, I don't want that, 63.4, and make sure you put the little degrees there, and you're done. And this does kind of look like 60 degrees from the positive x, so it looks like we're looking good, just eyeballing it. What about letter B? Where is that vector located? The vector negative 1, 2.
Third quadrant.
Third quadrant.
Negative
Second quadrant.
2 is in second
A
quadrant.
second, yeah.
That means there may be some trouble. Now the magnitude's not going to be any trouble. Heck, that's still going to be easy peasy, and it's going to be square root of 5. Fine. Same length as the other one. But the direction is going to be a bit of a problem because you're going to get to your calculator and you're going to go, how could my calculator be so wrong? You're going to go second tan inverse negative 2. Boom, what happens? I get negative 63.43 whatever degrees. But wait a minute. This angle here does not look like negative 60 degrees. Negative 60 degrees would be over here in quadrant 4, right? Negative 63.4 degrees. So what do? We add 180 to get us to the correct answer. So here, you've got your approximate like negative 63.4 or whatever and some change. You're going to add 180 degrees to it to get the right answer. So you go over to your calculator and you go, what? Plus 180 degrees, ding, and you go, 116 point, and if I'm going to round it to the nearest 10th, 0.6. And that looks like it's legit, because I'd buy that over 100 degrees here in quadrant 2. And we're done. There's the direction, we're done. Easy peasy. You're funny, Ara. It tweets instead of barks because it's bilingual. Could be. Good one. What kind of bird is it? Well, Jaime, my bird is a red-bellied parrot, and they're native to Africa. They're related to the Senegal parrots in Africa. They're known as poicephalus, grayheads. But my bird does not have a red belly. And you may be going, why? Is there something wrong? Yeah, my bird is a female. Females don't have the big orange red circle on their belly. Uh-oh, somebody's getting some flashbacks to physics. Yep. Speaking of physics, let's do some physics problems. Yay. And then we'll finish out today's lecture. So it's going to take me some time and I'm going to run through this. So resultant force. Suppose you have a large piece of granite and you've harnessed it to a horse that pulls with a force parallel to the ground of 1,000 pounds. Okay. And suppose you're simultaneously tugging at another rope, making an angle of 50 degrees to the horse's rope and with a force of 200 pounds. Give both the magnitude and direction of the resultant force. Now, resultant force means you got to add forces together. So this means, adding forces together. What's the result? So I'm going to draw a picture of what's happening. Okay, first I'm going to draw a big rock. Here's a big rock, big piece of granite. And over here, I'm going to attempt to draw a horse. Bear with me. Oh boy, this is not coming out as good as I was hoping. Oh well, shoot. He looks kind of squat. We're trying to make him look pretty, but oh man, I'm gonna have to give him longer legs. That looks a little better. Yeah, terrible. All right. You're gonna harness him up and then you're gonna connect him to this big rock. And the rock's sitting on the ground. Okay, so here we go. So you've got this horse, he's pulling with some force, 1,000 pounds. And then you're going to be standing over here pulling with another rope with an angle of 50 degrees to the horse's rope, and you're pulling with 200 pounds. Great. So how do you deal with this thing? What you're going to do is you're going to draw a force diagram. And when you do one of these physics type problems, your force diagram, you're going to have an X and Y axes. And so you want to pick, since you're the boss, where should you overlay the X and Y axes so it's easiest for you? And the easiest place is for the origin to kind of be right there. And there's the y-axis and there's the x-axis, like so, okay? And then you're gonna make it look a little prettier. This is kind of a hot mess and I apologize for the terrible drawings. Anyway, okay, so the force diagram, that's, remind me to take an art class. Okay. So here's what it's going to look like better. Okay, here's your X and Y axes. Your horse's force is going to be on the ground essentially because it's parallel. And in fact, since they told you it's 1,000, that's actually a nice thing. They actually gave you the length. So this tip right here is at the 1,000 mark on the X-axis. Great. We'll call this force F1. You are pulling with a force of 200 pounds, so your arrow isn't as long, it's only 200 in length, that's a magnitude. And the angle that these two vectors make with each other is 50 degrees. Let's call your rope force F2. So the resultant force that we want is F1 plus F2. And once we get that, we'll be able to figure out the magnitude and direction of that force. So even though I don't have that in hand yet, let's eyeball it. Remember that vector addition, if you use the parallelogram law, if these two vectors form adjacent sides of a parallelogram like that, and you can imagine the other two side lengths, the sum is going to be the diagonal of the parallelogram. So this green vector is the answer, is the resultant force. And I hope you can see from just looking at the picture, its magnitude is probably going to be a little larger than 1,000. And the angle that it makes with the positive x-axis is definitely going to be less than 50 degrees. We can definitely say that. Not exact, but that gives us an eyeball for the answer. So now we got to do the hand-to-hand combat. Okay, so step one is you want to get the component forms for both F1 and F2. And once you get those, it'll be easy peasy to add those two vectors together. Okay, and you're going to use some of the knowledge we used in today's lecture. Okay, so I hope you can appreciate that F1 is making an angle of 0 degrees with the positive x-axis. So his x component will be the magnitude times cosine of 0 degrees, and his y component will be 1,000 sine of 0 degrees, okay? Good news, cos of 0 degrees is just 1, so 1,000 times 1 is just 1,000, and sine of 0 degrees is 0. So there we have component form for the horse's force vector. Lovely. Let's go get your vector. Magnitude, 200 pounds. Cos, 50 degrees, which isn't going to be a nice number. And then the y component, 200 sine of 50 degrees. Yay. Also not going to be a nice number. Fine. So then what is F1 plus F2? And that is your resultant force. And we already know how to do vector addition. So we're going to add these two vectors together to get a big old vector. So when I add the two x components together, and I'm going to do some decimals now because this right here is, it's not a pretty number. It's 128.5575. And use a lot of decimal places. Don't round off until the very end. Otherwise, you'll propagate errors due to rounding. The second component, I got another weird number, 153.2089. I know. So when I add these two vectors together, I add the x components to get 1128.5575. And I add the y components together. Well, that other guy's y is 0, so not much there. And I get 153.2089. And now I can go ahead and get the magnitude. So the magnitude is going to be, and this is where you whip out your calculator and type it in. And don't forget to put parentheses around the radicand. Otherwise, you'll get wrong answers and you'll get all mad at me. I do give partial credit, but it's hard for me to give partial credit for incorrect typing in the calculator, okay? You're all scientists and engineers, and I'm sure you'll be able to figure this out. This is going to be, and I'm going to round to the nearest whole pound, although you may want to round it to tenths or whatever MyLab Math tells you to go do. It's roughly 1,100 pounds. And if the piece of granite had any feelings, that's the force it would feel on, pulling. 1,100 pounds. Whoosh. Now, what's the direction? The direction is the angle. And the angle is going to involve that tangent inverse of y over x, not x over y, be careful. So you're going to go tan inverse and then definitely whip out the calculator. 153.2089 divided by 1128.5575. Yuck. And I'm going to round to the nearest whole degree. I get roughly 8 degrees. And we're done with this problem. The two answers are magnitude, 1,100 pounds, direction, 8 degrees. That's the horse problem.
Can you scroll down real quick one more time? Oh yeah. I got it.
We don't have any friction, Rudy. We're not talking about the piece of granite moving. We're talking about the horse just pulling. And so we're neglecting any other forces involved. Yes, the hardest part about this problem is drawing the horse. I would agree. Yeah, work on your horse drawing skills. No, I'm just kidding. Come on. You have other things to work on in this class. Don't worry about drawing horses or anything else. Okay, let's do another physics problem and then we'll call it a day. Okay? And then you're free to go. If you need to go right now, go ahead. Just make sure you watch the recording. And I should post it later today. That's my hope. After I answer about 57 emails. Yeah, the first week of class is not easy. So another physics thing. Now, a lot of students, when they're watching these physics problems, they go, oh, all these physics things are the same. Be careful, this is not the same. This is a static equilibrium problem. So although it's going to involve a force diagram, that's where the similarity to the horse problem ends. Because the horse problem, you were given two forces and they just wanted you to add those two forces together and get the magnitude and direction. This is very different. Static equilibrium is defined as an object at rest. And so if you're doing a static equilibrium problem, you still have to figure out all the forces and you still are going to add them up. But once you add them up, you set them equal to the zero vector. Because the sum has to be zero vector. So we're going to neglect any torques or rotational forces or anything else going on in this simplistic problem that I have here involving cable tension. So if you look at this picture, you have some ropes hanging from the ceiling, and the two ropes are trying to support a 500-pound weight. Oof. So they want you to find the tension, and that's basically a magnitude of a force in pounds that each of these supporting cables is feeling, if they had feelings, which I know they don't. Okay, so since we're the boss and we want to convert this to a force diagram, we're going to overlay an X and Y axes on top of this picture, and we want to pick the best spot for the origin. We want to play the game like a smart rat. So I claim that the origin should be right there where it looks like all of these ropes meet, and then we'll have an X-axis and a Y-axis like so. So in order to avoid messiness, let me come over here. Okay. So I'm going to start drawing these forces. Let me draw the easy one first. This 500-pound weight is the force vector for it is directed vertically downward. And because they gave you the magnitude, the tip of the vector there is actually located at -500 on the y-axis. That's right. We'll call this F1. Great. Now, how about this vector here? That's cable 2. We'll just call him U. You can name him whatever you want. I have my notes I named with U. Okay. And then this other cable here looks like he's a little shorter. I don't know. Whatever. We'll call him V. Fine. So we need to get component form for all three of these force vectors, add all of them together to get one big old vector, set that equal to the zero vector. So here's my claim. Because of static equilibrium, all of these forces have to add up to the zero vector. That's what static equilibrium even means. And then we'll take it from there and do some algebra to finish out the problem. Yeah, algebra. Good stuff. So here we go. This angle is -90 degrees. So F1, if I use the formula that we do, you'd have, magnitude is 500, cosine of -90 degrees, comma, 500, sine of -90 degrees, fine. Cosine of -90 is 0, so your first component is a big old 0. Sine of -90 degrees is -1, so -500 is the y component. And I hope that was even obvious just by looking at the picture. You didn't even have to do the formulas here. But I did because I just want to make the point. How do we get the other formulas? So this U vector, one of the unknowns is the magnitude. I do not know what the magnitude is. In fact, once we get it, that's going to be one of the answers to this problem. That's the tension in pounds that cable is holding on to that weight to keep supporting it. But what about this angle right here? What is this angle? Does anybody want to look at our diagram and try to use some geometry to get this angle? Say again?
30.
Perfect. And the reason why is when you have two parallel lines cut by a transversal and they give you this angle over here, which they did, this angle over here has to match. So that's 30 degrees, bingo. So U is going to have this for component form, unknown magnitude, that's going to be one of our final answers, cos of 30 degrees, comma, magnitude of U, sine of 30 degrees. That's it so far, yikes. Now what about V? V is over here in quadrant 2, so the angle is going to be larger than 90 degrees, that's for sure. What is this angle here? Now, if you look at the diagram, they gave you this angle here, which is 70, but I don't think that's the angle that we want to use for the vector V, because we want the angle it's making with the positive x-axis. Any ideas?
That is the other angle is 70.
Yeah, this angle over here on the other side is 70 due to that two parallel lines cut by a transversal. But what about over here?
Oh yeah, that's 80, isn't it? It's 80.
Well, hold on a minute. We want it to be something larger than 90. 'Cause it's
110.
good, 110. Why is that? Because we're using supplementary. 70 degrees plus whatever our mystery angle is has to add up to 180 degrees total, right? Because this is 180 degrees. So you've got 70 on this side, so you need 110 to make it all add up to 180. Very good. So your V is going to be some unknown magnitude, that's a V magnitude, cos of 110, sorry, and then magnitude of V, sine of 110 degrees. Those are yucky numbers, let's leave them for now. Okay. Now it's time for, let's add them all together. So U plus V plus F1. What is that going to be? That's your resultant vector. So you're going to have a big old vector here. Let me leave a lot of room. And I'm going to add up all the x components of all three vectors. Just add them all together, okay? Magnitude of U, cos of 30 degrees, plus magnitude of V, cos of 110 degrees, plus 0, that was easy, comma, add up everybody's y components. Ding, 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 okay? Magnitude of U, sine 30 degrees, plus magnitude of V, sine 110 degrees, plus negative 500. Oh my goodness, what a mess. That has to equal the 0 vector, and the 0 vector simply has zeros for components. Don't set it equal to 0, because you don't want to set a vector equal to a scalar. That would be a silly mistake. A vector equal to a vector. And the 0 vector looks like that. Okay, now, good news. Remember I told you equality of vectors will come and save us? Here it comes to save the day. If this big old vector on the left side has to equal the vector on the right, their components have to match. The components must match because of equality of vectors. Oops, I can't spell either. Much math. I don't even know what I'm writing anymore. Must match, sorry. So let me write that down. The magnitude of U, cos 30 degrees, plus magnitude of V, sine, or cos, sorry, I'm getting ahead of myself. Trying to go too fast, that's the danger of trying to go fast. Cos 110 degrees, that has to equal that guy's x component. And now you equate the y components. I need magnitude of U, sine 30 degrees, plus magnitude of V. I have a delay right now, it's hard. Sine of 110 plus negative 500 has to equal 0. And folks, this is a linear system of equations. You learn how to solve these in your algebra class. I'll walk you through some of it and then I'll kind of skip a few steps, but I want you to see it. So find the unknowns. What are the unknowns? Magnitude of U and magnitude of V. When you took an algebra class, oftentimes your unknowns were like X and Y or something like that. but this is really the same as that. But you do have some weird numbers. So I'm going to rewrite equation 1 and finally fill in the numbers. So cos of 30 in decimal is 0.866. You're going to multiply that by magnitude of u, plus cos of 110 is negative 0.39 or 342. That's a 4. 342 times this unknown magnitude, that equals 0. And for equation 2, I'm going to add 500 to both sides. So the 500 is on the right. And then I'll put in the weird decimals. I'm going to have sine of 30 is nice. It's just a half. So 0.5 times magnitude of u plus 0.9397 magnitude of v equals 500. There's 2 equations and 2 unknowns. I'm going to use the substitution method. I'm going to solve equation 1 for the magnitude of u. And that's pretty easy because you'll just use a little bit of algebra steps. So I'll add that second term to both sides. So I'll have 0.342 magnitude of v. And then I'll divide both sides by 0.866. Yuck. That looks horrible. Well, you're going to substitute this in place of the magnitude of u in the second equation. Well, that's why they call it the substitution method. Okay, and everything else stays the same in that second equation. I know. It's pretty yucky looking. So when you substitute that weird quotient for your magnitude of u, and I'll just put it in here. I know. And you're going to have your calculator ready. Because the good news about this equation, it only has one unknown. It's the magnitude of v. Granted, it's got a lot of weird numbers in it, but use a little bit of algebra and then finally isolate the magnitude of v and solve for magnitude of v. And I get approximately, because I rounded it in decimal form here, approximately 439.7, and the units are pounds. And that's the cable tension in the cable that I labeled V, which is cable 1. Cable 1 is feeling 439.7 pounds. Otherwise, it'll snap. So that's one of the answers. And then we got to get the other answer. How do you get magnitude of U? Well, we got magnitude of V, so if we plug it right there, since we already have magnitude of U written out in terms of magnitude of V, good news, punch it up in your calculator. And I get the magnitude of U is approximately 173.6 pounds. And there's the other answer. So you got your 2 answers because you got your 2 unknowns. Yay, physics. Success.